Hello everyone. So welcome back to our latest lecture session. So thus far we have been discussing acids and bases, and we are done with that, right? So now we are going to move on to the other major aspect, or one of the other major aspects in our environmental chemical process, and that's going to be the formation of, or aqueous complexes, I guess, right? So we are going to talk about aqueous complexes here. Before that, a quick 2 or 3 minute review about what we have been up to thus far, and how the discussion about aqueous complexes fits into the bigger picture, right? So let's have a look at that. So again, we talked about the basic aspects related to any chemical process. So that's equilibrium, right? We discussed that, and we also talked about kinetics. Yes. So how far can the chemical process go to, let's say, and how fast, right? How far and how fast. And in that context, we mentioned that we usually have 4 kinds of chemical process that an environmental engineer would come across, right? So one is obviously the acids and bases, upon which we have spent considerable time. So acids and bases are what do we say, relatively fast reactions. So that's why the applications of kinetics in acids and bases are negligible, but equilibrium is what you would almost always observe or achieve. So thus we looked at relevant aspects with respect to acids and bases after the system reaches equilibrium, right? So that's what we discussed in great detail: strong acids, weak acids, bases, acid neutralizing capacity, right? Base neutralizing capacity, alkalinity, which is something remarkably important because it is omnipresent, I guess, right? And we had applications with respect to Wehm intake and so on. So we talked about acids and bases, and so now we are going to move on to complexes. Yes. And then we are going to talk about precipitation and dissolution. Yes. And then the last major aspect is going to be redox. Anyway, we are going to spend relatively less time on complexes and precipitation and dissolution, and more time acids and bases and redox reactions, I guess, right? So the reason for looking at this holistic picture is, most chemical process can be, very broadly classified based upon 2 aspects, let's say, right? Again, what drives a chemical reaction now, let's say, or a chemical process now, right? It's because the relevant molecules or atoms involved would want to have a more stable structure or form with respect to their, the outer shell, right? Arrangement of electrons in the outer shell, they would want it to be more stable. So all the chemical processes are driven towards that particular aspect, right? So that, it's more stable. Yes. So in general, we can broadly classify, these chemical process into 2 aspects. One where the oxidation state or oxidation number or oxidation state of the relevant atom or such would change, and that obviously is the redox process, when the oxidation state would change. And the other aspects, as in acid bases, complexes, and precipitation and dissolution, these come under the process where just the coordinative, I can call that coordinative relationships, I guess, right? So the 3 aspects, as in acids and bases, complexes, and precipitation and dissolution, you obviously would not see any change in the oxidation state, but you would see a change in the coordination number, let's say, right? Or the coordination partner would change. Again, there is no change in the oxidation state when the relevant reactions are acid base or complex formation or precipitation and dissolution, right? It's more or less they are based on coordinative relationships, right? And again, that's what I'm trying to point out here. So let's move on and look at it in great detail. So for now, we are going to talk about complexes in greater detail for maybe a couple or of classes, or probably 3 at the most, right? So let's look at why they are important first before we go into any other aspect. So we need to look at why, as an environmental engineer, am I concerned with it, let's say. So in general, we as environmental engineers would need to look at complex formation, or consider that whenever you have any particular system that deals with metals, let's say, right? So obviously, if you have a heavy metal, you are concerned with its removal or remediation or such, and aqueous complexes play a remarkably important role in that particular context. or just say, let's say if you're adding a coagulant, let's say Fe2 plus, Al3 plus, Fe3 plus. Again, aqueous complexes are formed and they play a remarkably important role in those scenarios where you come across let's say metals, let's say, right. So again, before we go further, let me just demonstrate what it is I am trying to look at. So I am going to look at V-Mintech here, and before we go further, so I am going to put in, I have two forms of what do we say, iron, Fe2 plus and Fe3 plus that I am going to consider, right. So I am going to put in a random concentration of Fe2 plus and also a random concentration of Fe3 plus in V-Mintech, right. I am going to substitute them or plug them in V-Mintech. Ferrous and ferric, I am going to plug them in at different concentrations, and I am going to compare in what states are they going to exist. So let us look at, let us say, different pH values too, you know, let us have, let us say, pH 3, 7 and let us say 11, okay. So let us just look at this, you know, I am just trying to demonstrate, let us say, what it is that I am trying to talk about here, right. So let us switch to V-Mintech here. So first I am going to go to, let us say, fixing the pH at 3, right, and where is the key here, 3, and I am going to put in Fe2 plus, and where is that, let us say, Fe2 plus, right, and let us say I will say millimolal and maybe 1 millimolal, let us say, okay, and how come 1 millimolal, add to the list, right, and view edit list. So 1 millimolal, okay, I should have put in something with respect to, so let us say what should be my source, let us say it is going to be FeSO4, let us say, right. To balance the charge, let us say I am plugging in, I am putting in FeSO4, right, FeSO4, right. Yes, and it is going to be source for Fe2 plus and SO4 2 minus, right. Let me plug that in here. Anyway, relevant equivalent concentrations, right. So I am going to plug that in, view edit list, back to main menu and run Mintech, right. So now let us say I have the relevant concentrations at pH 3, okay. So now you see that, you know, you have Fe2 plus and you have FeOH plus, FeOH twice and FeOH thrice with a negative charge, right. So Fe2 plus is present in different forms here, right. So that is what I am trying to look at, let us say, right. And what are the complexes here that I am talking about? So here I have 3 complexes that are formed here. So the ferrous iron, right, or ferrous is forming various complexes with OH minus, and we see that we have, I think, for that particular concentration and that particular pH, we have the relevant concentrations, right. So anyway, what I am trying to say is we have, let us say, when we put in ferrous and the solution, it does not stay only as ferrous, right, it stays as either FeOH plus, Fe2 plus, which is its free metal, this is the free metal, and these 3 are the complexes. So if I want to look at the relevant concentrations or relative concentrations, pardon me, so I am going to look at view species distribution. So it looks like, here they are not giving it to me with respect to the breakdown. So again, they are saying that Fe2 plus will be present as in different forms as 90% of it in different forms, and this does not give me a great idea here. So I am going to go back to the main menu. So again, if I look at the total concentration of Fe2 plus, it is present as FeOH twice, FeOH thrice, negative charge, Fe2 plus, FeOH positive charge and FeSO4, right, but it is present as free metal only at this particular concentration, right, but that is it at pH 3. Let us see what would happen if I increase the pH. Keep in mind that the free metal concentration is relatively high compared to FeOH and the other 2 complexes, I guess, right, or different orders of magnitude. So I can neglect the concentration of the complexes. So if I increase the pH, what would I see here? So I am going to increase the pH to, let us say, 7 now, as we just talked about earlier, and I am going to run Mintech, and now let us say Fe2 plus concentration is still relatively similar, but the concentration of the complexes, right, 1, 2 and 3 complexes, they have relatively increased. Why is that? So we are talking about complexes here, metal and ligand. We are going to discuss this later. I am just trying to explain a few or help you visualize what it is that we are going to talk about. You have a metal which is electron poor compound, and you have a ligand which is an electron rich compound. So a complex is nothing but, let us say, a soluble species formed by a combination of an electron poor compound which is the metal and a electron rich compound which is the ligand, right, between an electrophile and a nucleophile. Again, we are going to discuss this later, but keep in mind, for a complex to be formed, you need a metal and a ligand. A metal means it's electron poor, and ligand usually is electron rich compound, right. So again, here you see, because you increase the OH minus concentration, right, when you increase the pH from 3 to 7, what's happening? You are increasing the OH minus concentration. So obviously the Fe and OH, what do we say, complexes are going to be at relatively high concentrations, but you still see that compared to the free metal concentration of Fe2 plus, FeOH and FeOH thrice, twice are still at relatively low concentrations. So again, I am now going to change the pH to 11, right, pH 11, right, and I am going to run Mintech. So again, I guess you still see a further increase in your particular complexes, right, FeOH plus, FeOH thrice and FeOH twice, and now you see that the actual free metal concentration is much lower, right. So as you kept increasing the pH of your solution, and you are looking at the speciation of Fe2 plus, right, and if you are considering the various complexes formed at pH 3 and 7, you saw that the free metal was predominant in the solution. But at pH 11, what is it that you are observing? You are observing that the complexes FeOH, FeOH thrice and FeOH twice, they are almost 2 orders of magnitude higher than the free metal concentration, right. So this is what you need to keep in mind, because you know free metal concentrations are what we let us say might consider depending on the scenario. So depending upon the pH, or in this case the ligand concentration, ligand here is OH minus, right. Depending on the concentration of ligand or the type of metal, you know, your speciation or the relative concentrations of your complex or just the free metal, they are going to change, right. So this is with respect to Fe2 plus, just keep that in mind. So now we are going to run the trial with respect to FeCl, FeCl3. So we put in a source of FeSO4, that is why we plugged in Fe2 plus and SO4 2 minus, right, and if I am putting in FeCl3, that is going to dissociate into Fe3 plus and Cl minus, right, 3Cl minus, yes. So that is what I am going to plug in now. I am going to check, why am I trying to do so? Earlier I plugged in FeSO4 to see what complexes can Fe2 plus form. Now I am just trying to illustrate to you what are the complexes or what is the behavior of Fe3 plus. You know, now we are going to look at some particular relevant aspects, I guess, right. So go back to the input menu, right. So I am going to again start with pH at 3, pH at 3, and now I need to edit the list. I am going to delete Fe2 plus and SO4 2 minus and back to main menu, and now I am going to plug in Fe3 plus initially, and where do we have Fe3 plus? That is here. Again I will stick with 1 millimolar, add to list, and then Cl minus, right, Cl minus, okay, and that has to be 3 though, right, 3 millimolar, and I add that to the list. The pH is at 3. Let me check my components Fe3 plus and Cl minus, okay, and I am going to run Mintech, and let us look at the output now. Okay, at pH 3, and I have free metal concentration here Fe3 plus, right, 1 into 10 power minus 4, right. Earlier we had 1 millimolar, and now keep in mind that is almost a tenth of it even at low pH, right, 10 power minus 4. 1 millimolar was 10 power minus 3 concentration total, but here you see Fe3 plus can form a lot many more complexes, as in let us start with FeOH. Do we have that somewhere here? Okay, we have that here, FeOH 2 plus charge, right. Anyway, you have multiple complexes 1, 2, 3, 4, 5, and with Cl minus 2 it can form a complex again 6. So what you see is Fe3 plus can form a lot more complexes. So even at low pH, right, if you look at that, the free metal concentration is considerably affected, right, and some of the complexes like FeOH twice plus 4 charge, is it? No, Fe2OH twice plus 4 charge are as high in concentration as Fe3 plus, and also look at FeOH twice or FeOH twice, right, FeOH with 2 plus charge. you see that it's 10 power minus 4 concentration, it's greater than the free metal concentration. For Fe2 plus, you saw that at pH 3 or 7 the free metal was predominant, and only at pH 11 was the free metal concentration relatively lower. But for Fe3 plus, you see that even at pH 3 the concentration of the aqueous complexes that Fe3 plus forms are higher than or relatively comparable to the free metal concentration. So let's go back to pH 7 scenario. I am going to change this to pH 7, and here pH 7 and run Mintek. So again same case, I am going to look at the relevant concentrations. So now you see that Fe3 plus is now at 10 power minus 12. Earlier at pH 3 it was at 10 power minus 4 concentration. So now again you see that the complexes are at much higher concentrations, right, and predominant complex is FeOH with 2 plus charge. So again what does this tell you, right? So if you put in a source of Fe3 plus, let us say at pH 7, it is not going to stay as Fe3 plus, right, it is going to form multiple complexes, right, and one of those complexes is going to be predominant in concentration. So let us say if you have some other reaction that depends on the free metal concentration, is that going to be relevant? Not really. Why is that? Because the free metal concentration or Fe3 plus staying as Fe3 plus is remarkably less, which is 10 power minus 12 in this case, and one of the complexes is at a concentration of 10 power minus 4, right, 8 orders of magnitude higher, right. So that makes a critical difference, right, in your particular system or the interactions therein. So again obviously if I keep increasing the pH to pH 11, obviously again that trend is going to worsen further, as in free metal concentration is still going to be pretty low, and the aqueous complexes here, because I am only changing pH or the ligand concentration, which is OH minus here, that is why we are looking at only a few OH. Obviously you can have a metal and different ligands too, as in here I guess we even had Cl minus, I can call that I guess as a complex 2, right. So let us go back, change the pH to 11 and run Mintek, and what do I see here? And I see that Fe3 plus concentration is now almost 10 to the power of minus 13 times lower than what it was at pH 7. So what does this tell you now? That maybe Fe3 plus would stay as Fe3 plus at lower or acidic pH, but in neutral or basic pH, right, or basic solutions, the free metal concentration is going to be negligible, right, but only the concentration of the complexes is going to be relevant. So which complex is predominating here? FeOH 4 with the negative charge is what seems to be predominating, and it more or less is equal to 10 power minus 3, right. 1 millimole was what we put in initially of Fe3 plus. So here it shows us that FeOH 4 with a negative charge, right, is almost equal to the total iron that you put in initially. Makes sense hopefully, right. All the free metal or that you initially plugged in is now present as this kind of a complex, yes. So any interactions or any reactions that you think might occur with that particular Fe3 plus, right, they are now going to be negligible. So again this is what we are going to talk about. So I just took an example of ferrous and ferric iron to illustrate the example here. So let us go back to our particular case, right. So Fe2 plus, we saw that it is at considerable quantities at pH 3 and pH 7 and so at pH 11, but Fe3 plus is at considerable quantities only at pH 3, and at pH 7 and 11 it is at remarkably low concentrations, right, and that is what we observed here. So again Fe2 plus is in general does not form a lot of complexes as you just observed, but Fe3 plus rarely stays as free metal, right, it forms complexes. So that is one particular aspect. So again so let us again take a look at the bigger picture. So for forming an aqueous complex you need a metal and a ligand, and a metal is an electron poor compound, let us say, and a ligand is an electron rich compound, right. So thus you need a combination of these two, a metal and ligand, to be able to form your relatively more soluble species, which is your aqueous complex, right. So let us go further and discuss some of the basic aspects. So if we remember our particular definition for Bronsted acid, how did we define acids in our acids and bases? We mentioned that there would be H plus donors, right, but in the same case we also looked at Lewis acids, right, and we define them as electron acceptors, right. So, here we can understand the aqueous complex formation in terms of Lewis acids or bases or electron acceptors or donors. So, let us look at one example here, let us see. So, one of the examples I guess I have here is Fe3 plus H2O. So, if I put in Fe3 plus into the solution and H2O, right, and let us say at a particular concentration or such, it can or it will be in equilibrium with FeOH, and thus the charge is going to be 2 plus, and now it is going to obviously release the H plus. So, going by the definition of Bronsted acid, Fe3 plus can act as an acid because it is leading to or it is donating a proton here, it is ending up increasing the concentration of H plus, right. That is why you can call that as a Bronsted acid, or obviously as a Lewis acid because Fe3 plus, which is electron poor, will pull the electrons from the oxygen, right, atom, yes, and form a complex, yes. Again it is accepting the electron here, let us say in a way, and that is why you can call that a Lewis acid too, makes sense hopefully, right. So, here you have electron acceptors. We if you remember or refresh your memory, we looked at acids under two definitions. One is Bronsted acids, where we say if a particular compound is donating H plus, we classify that as an acid, or if it is accepting an electron, we can call that as a Lewis acid or an acid, let us say. In general, Bronsted acids are a subset of Lewis acids. So, obviously here the example we have here is Fe3 plus addition to water, right. So, Fe3 plus is electron poor and oxygen is electron rich, right. So, it accepts the electron, let us say kind of accepts the electron, that is for your particular understanding, let us say, right, and it forms the complex FeOH with a 2 plus charge, and in the process releasing H plus, right. So, this is one particular example that we look at. So, obviously what do metals look for, let us say, because they are electron poor, that means they are electrophiles, right, and ligands are electron rich or nucleophiles, right. Phile means you have a tendency to, I think, attract or such. You can look at the definition for the root word. Phile means, so metal, when we saw it is an electrophile or electron phile, so it wants to attract electrons, right. So, our is an electron acceptor. So, that is what we look at. So, your aqueous complex, you need a metal and a ligand, electron poor and electron rich, and you will end up forming a complex, let us say plus Z and minus X charge. I am just going to say a generic term is the charge is Z minus X, right. And in general your aqueous complexes are relatively more soluble, right. The aqueous complexes are relatively more soluble, keep that in mind because we are going to look at that later on, I guess, right. So, let us move on. We are going to look at a few terms, I guess, and with respect to terminology, what is a complex? Obviously it is a soluble species and it is formed by a combination of electron rich compound, which is the ligand, and electron poor compound, which is the metal. So, three aspects here. First, it is a more soluble species and you need an electron rich compound, which is your ligand, electron poor compound, which is your metal, right. And ligand, generic example, water, you have OH minus, but you have various other ligands, right, Cl minus, CO3 2 minus, and so on, yes. Anyway, let us look at what else we have here. So, you need an electron, we have something called central atom. So, that is the electron poor compound in your complex, which usually means it is the metal, right. So, central atom is the metal here in general, electron poor compound. Next aspect is ligand, it is the electron rich compound in the complex. This is something we discussed earlier, electron rich compound in the complex. And here now we come to our particular aspect, a coordination number. So, coordination number gives us an idea about number of ligands per the central atom, right, and that helps us in understanding the structure, right, of your compound. Again, if you remember, we classified acids and bases, aqueous complexes, and what else now, precipitation and dissolution are as being based on coordinative relationships, right. In that case, we also talked about coordination number and such. So, coordination is nothing but number is nothing but in the context of aqueous complexes, number of ligands per central atom. So, it can have different numbers. So, based on the different coordination numbers, you will have different structures. So, let us look at some of the usual coordination numbers and the structures, right. So, if you have two ligands per one central atom, right. Usually we have a linear, right, a linear complex, and this is the structure that you would observe. Yes, 2, and in general most of the complexes you have would have even coordination numbers. Some might have 5, but that is relatively rare or very rare though. Usually you will have 2, 4 or 6. So 2, it is going to be linear, right, and that is what we see here. And if it is 4, there are 2 kinds of shapes or 2 structures, I guess. One is tetrahedral, right, with L, L, L edges of pyramid, and central atom, the metal is here, and the other ligand here, more or less a pyramid, right, an equal distance, I guess, or equidistance between the metal and the ligand, or the central atom and the ligand. So tetrahedral shapes, usually more stable. And the second aspect or second kind of shape with 4 central atoms is the square planar, again self explanatory, in the same plane, 4 ligands per central atom. So the coordination number is 4 and square planar, I guess. And 6, obviously, so we have an octahedral shape usually, with 4 in one plane and L above and below, right, 4 ligands in one plane, and the other 2 ligands, one above and one below. So again, what is the coordination number? Number of ligands per central atom, and central atom is the electron poor compound in your particular complex, right, and that is what we looked at here. We usually come across what we say complexes with coordination numbers of 2, 4 or 6, right. So let us move on and look at what else we have here. So a few terms, nothing to mug up, but so let us say if somebody is speaking about it, you need to be able to understand what it is that they are referring to, right. So we have a few what do we say terms here, monodentate, multidentate and so on. Let us see what it is that we are about. So monodentate is when we have one electron rich structure per ligand, right, more or less it means one binding site. So if it has, your particular structure has, electron rich structure has one binding site, you would call that a monodentate. Obviously if it is more than one, right, if you have more than one electron rich structure, you would obviously call that to be a multidentate, and obviously they will tend to be stronger, right. So monodentate, bidentate, tridentate and so on more or less means either one binding site, 2 binding sites or 3 binding sites and so respectively, right. So the next aspect would be looking at chelate. Chelate is a complex, first understand that it is a complex which is formed with a metal or a couple of metals, let us say, or more than a few metals, and is multidentate, I guess, right. So it is a complex that has more than, or that involves more than one binding site, and these are called chelates, and they are relatively more what is it now, stable. Yes. So let us move on. So again, what is the importance of this particular aqueous complexes now, right. So we will briefly touch upon that for today's session. So again, we are talking about metals. So let us consider 2 aspects, let us say. One would be, let us say, we are talking about heavy metals, and in this case let us say we are talking about total concentration of metal is not equal to the concentration of free metal. That is what we discussed earlier when we talked about Fe3 plus and Fe2 plus, right. For example, I put in Fe3 plus, total was 1 millimolar, right, but I saw that at different pHs, either 3, 7 or 11, my actual Fe3 plus concentration, Fe3 plus total is still constant, it is still 1 millimolar, but Fe3 plus concentration was decreasing and further decreasing with increase in pH. And why is that? Because the concentration of the complexes was increasing. For example, let us say, to simplify that, Fe3 plus total or Fe3 total, let us say, is equal to the free metal Fe3 plus all the complexes, let us say, right. So obviously here for Fe3 plus though, we saw that in general the concentration of the complexes is much higher, right, and the concentration of the actual free metal is relatively lower, but obviously the total free metal concentration is going to be constant, let us say, right. So let us say, with this in mind, let us say, when is this an issue, let us say, right. Let us say you have a heavy metal, right, and let us say the free metal is toxic, right. If your free metal, right, is toxic, so then let us say how would your particular system be affected by formation of complexes now. So keep in mind that let us say for that particular system or for that particular heavy metal, pardon me, if the free metal is what is toxic, and if you add ligands, right, what is going to happen? You are going to have complexes being formed, And what will that lead to? It can lead to the decrease in the free metal concentration, right. So, let us say initially we had only, let us say I will consider some metal x, x total was equal to the x free metal, let us say plus z, let us say, or plus m charge, okay. But after adding a ligand, what can it happen? X total, right, will be now equal to x1 m or free metal concentration, which is going to be lower, because now I am going to have formation of complexes, right. So, thereby you are reducing the free metal concentration, thus the toxicity of the particular solution decreases. So, with that, I guess I will end today's session, and we will continue this forward. We will talk about or have a brief discussion about the importance, right, how sorbability is affected and so on, and also look at some of the practical applications with when you would come across in titration, and then move on to the equilibrium aspects and so on, right. And with that, I end today's session, and thank you.